Okay, good afternoon. I'm Bart Cruz, Chief of the Research Division, and it's my pleasure to welcome you to today's Chairman's Air Pollution Seminar. We have the pleasure of having three close friends and some ex-colleagues here from ARB. They can give us an overview of the Department of Energy study on the differences between diesel and gasoline PM emissions, both in ambient air as well as tested out of the exhaust. We have three jam-packed presentations, so the way we're going to run it is we'll have each speaker go in turn, and we'll have 5 minutes of questions, and at the end we'll open it up to general questions and stay a bit later if we need to. Our first speaker today is Dr. Doug Lawson. He's a principal scientist at the National Renewable Energy Laboratory in Colorado, but that's only the latest stop on a long and distinguished career in industry as well as in government. Doug's well known to all of us. He was one of my supervisors and started some of the research programs here at the Air Resources Board and acid deposition, as well as major field studies we do for air quality. Doug's now a regulator and a scientist, lives in Colorado and is part of their commission or their equivalent here to the Air Resources Board. So great pleasure to introduce Doug again to all of you.
Thank you, Bart. On behalf of Eric and Jamie, we want to thank you all for allowing us to make this presentation today on our gasoline diesel PM split study. We've done a lot of work on this, and we'll go through the presentations, and we appreciate your being here. Again, we'll have questions at each presentation. First, I'd like to acknowledge our sponsorship of this study. It was sponsored, and the funding was provided by U.S. Department of Energy. James Eberhardt from the Office of Freedom Car and Vehicle Technologies was our program manager, and we've had additional support that came from Ralph's Grocery, U.S. EPA, the Bureau of Automotive Repair, South Coast AQMD, and ARB. The objective of this study has been to characterize uncertainties in quantifying contributions of PM emissions from spark and compression ignition engines in the South Coast Air Basin. And we, in addition to the support, we had several participants, Bureau of Automotive Repair and South Coast District, that did light-duty vehicle recruitment for us in this project. Ralph's Grocery provided the pad for us for which we could do the dynamometer testing for both the light and heavy-duty vehicles. And then EPA and their on-site contractor, CavTech, which is now called BKI, did the light-duty dyno measurements. West Virginia University did the heavy-duty dyno measurements, and then DRI and University of Wisconsin-Madison did the chemical analysis and source apportionment. So it was a large study with lots of groups. One thing that we've learned in these different studies over the years is to do concurrent ambient measurements while the source measurements are being done, because what happens is technologies change, fuels change, and we need to have the direct influence of those source types and what they're doing to air quality. So we do concurrent measurements of source types as well as ambient measurements. And so an approach that we've taken over the past roughly 10 years in our field studies is to spend a lot of time. In fact, I felt we need to spend more than half the resources just on doing source testing. So we did a source testing of a large set of gasoline and diesel-powered motor vehicles using these two transportable dynos, and this was done from May to September in 2001 over roughly a 4 to 5 month period. Then at that time, those samples were being collected. Ambient measurements were done at a number of sites over about a 4-week period, at fixed sites and several different sites in the basin. The chemical data then were collected from the source and ambient samples, and the analysis was done at University of Wisconsin and DRI. And some of those analyses were done collaboratively, but some of them were done independent of one another. And then finally, the source profiles and CMB modeling was performed, and that was done blind, so that both groups that were doing the source attributions could use their own approaches toward doing source apportionment. And then we're involved with submitting these papers for peer review, and that's being done right now. Now, I want to mention a few of the features of the study and then some caveats that we have. First, this study was done in the summertime in the LA Basin, as you know, and when putting this study together, I felt it would be best for us to do it in Los Angeles in the summertime to provide the greatest amount of challenge for the receptor modeling that would be done. Number one, because in the summertime you have very little cold, what I call cold start. And we've learned in some studies that we've done recently that especially for spark ignition vehicles, under cold ambient conditions, they emit much more PM than they do at, say, warmer ambient temperatures. And so we wanted to challenge the researchers here in doing the modeling to not have so much of what I call a cold start influence from spark ignition engines, but rather warm summertime cold start. And finally, in the summertime in the LA Basin, there's a potential for a lot of secondary organics to be formed, which would make the CMB analysis much more complicated. And so I wanted to really challenge these methods by doing it in the summertime and to avoid the cold start that you can get from spark ignition vehicles. Also, another caveat is that the vehicles were sampled as is. And so these are on-road or recruited vehicles. And recruitment is a big issue in these different studies, and trying to get vehicles that are on-road and really represent what is being driven. And that's a big challenge, as we've learned over the years. These results represent the on-road fleet characteristics and ambient data during the summer of 2001. And we know that future regulation, the 2007 and 2010 regulations for heavy vehicles, are going to really reduce on-road emissions, a heavy part of the fleet. So again, these results would be applicable to 2001. And we add a strong caveat here in this last bullet, and that is the mobile emissions profiles from this study should not be used in other parts of California or under cool or cold ambient temperature conditions, especially because of what the cold start does to PM emissions. And we didn't measure cold start conditions. And these profiles from the study shouldn't be used in other parts of the country until it can be conclusively demonstrated that the profiles that one would have from mobile sources would be identical to what we have in this study. So the burden of proof still remains as to how useful these profiles can be in other parts of the country and other seasons. Now, in these different studies that we've done, we've really focused again on getting good source samples. And so in this study, we recruited a number of light-duty vehicles. These were tested in June and July of 2001. And we tested 57 light-duty gasoline vehicles and 2 light-duty diesels. And they were divided among 10 different categories for the gasoline vehicles. The first 9 were based upon model year and odometer readings. And we attempted to get new vehicles with low mileage, new vehicles with high mileage, older vehicles with lower mileage, and older vehicles with high mileage. And the data set tended to emphasize older vehicles because we thought they'd have higher PM emissions, so we wanted to characterize that part of the emissions distribution quite well. We also had a smoker category, and those vehicles were recruited because of that they were supposedly smoking vehicles. And then we had a couple of light-duty vehicles. Number of vehicles in each category and the number of chemical composites that were made from these are also listed. Again, the newer vehicles have much lower emissions, so it's hard to get enough sample to do chemical analysis, so we had to have several vehicles and tests done to composite the data. Once the vehicles were recruited, they were given a smog check, and I'll tell you a little bit about that in a minute. And they were conditioned prior, and that was part of the conditioning process to get the vehicle acclimated to the kinds of driving conditions that we'd be doing. Once they were given the smog check and verified, then they were tested on EPA's transportable dyno, and they were given the unified cycle, the LA92 cycle, which is a higher speed, more aggressive test, and that's been developed here at ARB. The vehicle's exhaust was measured by quite a variety of methods, and this just is a picture of the different kinds of equipment that was used to measure PM and semi-volatiles. Quite a variety of different measurements that were made, including optical measurements of the exhaust as well. This may not be very visible to you, but this is the time and speed trace that was of the unified cycle. Normally the unified cycle has 4 different phases in it, but we took those 4 phases and divided it into 2 phases, a cold phase which was 1,400 seconds roughly. The unified cycle then has a 10-minute warm soak, where the vehicle is just shut off and rests for 10 minutes, and then it's given another warm phase test of another 1,400 seconds. And so we'll talk about a cold phase and a warm phase. The tests are the same. It's just essentially looking at the difference between the two as the emissions that can be attributed to the cold start. There were two phases, like I mentioned, a cold phase and a warm phase. The average speed in that test is about 25 miles per hour with about a 70 mile per hour maximum speed, about 7 miles per hour axle. And the summary statistics of the vehicles in this data set, the minimum reading that we had was 0 milligrams per mile, a very low emitter, at least couldn't be measured very well for PM. Maximum was 185 milligrams per mile under one of the tests. Now, in the study, we didn't get very many high PM emitting vehicles, and we could have done better on that to understand more about those, but we didn't get very many high emitters, even though we recruited some smokers. I've had one study where we had actually recruited a car that was emitting a gram per mile of PM. So they're out there, but it's hard to get them. The mean of these data was 19 milligrams per mile. The median was 5. The mode was 0, which again is a skewed distribution when you get those three statistics being very different from one another. Now, the vehicles that were recruited, the Bureau of Automotive Repair recruited those 9 vehicle categories. These were vehicles that were due for their smog check. The EPA contractor recruited the smokers and diesels. We offered incentives, $200 for each motorist and a free rental car during the testing period. And we gave them $50 if we rejected their vehicle. And then if they failed their smog check, which was given to them right on the spot, they were offered up to $500 in free repairs. So we tried to really have some good incentives. We recruited 74 vehicles, 15 were rejected. 6 were rejected because that particular category was over-recruited. 4 had engine or exhaust problems, and 3 were too large or incompatible with the dyno. 2 were rejected for other reasons. One of them had an engine rebuild at 230,000 miles, so it didn't fit our categories that we had. And then another case, the owner brought in the vehicle on the wrong day. Now, we had a couple other vehicle problems in those that were recruited. One of them overheated on the cold phase of the unified cycle, so we couldn't use it. And another one, its brakes caught on fire during the cold phase of the cycle. And so, again, these are real-world vehicles, and that's what we saw. 33 of the vehicles passed the smog check, excuse me, and 24 of them failed. 7 were categorized as gross polluters, and 5 were tampered with. Excuse me. And then there was 196, a newer vehicle, that failed the smog check but didn't have its mill illuminated, so it was what we would call an OBD false pass. And then also we had 2 that aborted their smog check inspections. Is there a way to get some water? Okay, thanks. Now, these data here are the scatter plots of the CO versus PM and hydrocarbons versus PM and NOx versus PM for these vehicles in the study. And one thing that we see with this data set that we hadn't seen for others is that we get a pretty good correlation for hydrocarbons versus PM. We haven't really seen that so much with other fleets. The correlation for CO and NOx versus PM is not so good. Now, on the heavy-duty side for this data set, we actually tested 34 heavy vehicles. 32 were trucks, excuse me, and 2 were transit buses. And these were recruited according to their year of manufacture and their gross vehicle weight. So of the 8,500 to 14,000 gross vehicle weight, we had 8 vehicles. Intermediate weight was 8. And then we had 16 of the heaviest vehicles, again, by different age group and category. Now, also, excuse me, we have, this shows the different cycles that were used for the vehicles. Thanks. In this data set, we had vehicles listed in red, and these are the vehicle numbers that were tested. So, for example, we had one vehicle in this box number 1, and it was given the test cycle set C, which was the CSHVR, the City Suburban Heavy Vehicle Route, and also the Highway Cycle and Idle Test. So each one of these different vehicles was subjected to a number of different test cycles. They were tested with California diesel fuel, and then 5 were tested with federal fuel. And this is a picture of the vehicles as they're tested on the heavy dyno. This is a schematic of the 4 test cycles that were used in the study, the CSHVR, the highway cycle, the urban dynamometer driving schedule, and then also the Manhattan cycle. Manhattan cycle is used to test transit buses, and so you can see the speed and time traces of these vehicles are very different. Again, because the heavy vehicles have such different types of driving patterns, it's not clear which driving schedule is the best one to be used, so we used a variety of them to represent different driving conditions. This is a schematic of the type of ambient sampling that was done during the study. There were a number of fixed sites at San Dimas, Azusa, and downtown LA. There was also some fixed sampling that was done at Dodger Stadium after a soccer game, and Eric will talk a little bit about that. And then these other traces show the freeway conditions. There was on-road measurement done at a variety of locations in the basin, both surface street and on freeway at different times of day. There were data collected in areas that should be heavily impacted by diesels down at the ports of Long Beach and Los Angeles, and also over toward Venice Beach where you would have fewer trucks, again to get a variety of different source regions and what the PM would look like in those areas. I'm going to present some of the data for second-by-second data from the study, just so you get a flavor of what we got. This graph is vehicle number 1, a light-duty vehicle, a Toyota, had about 50,000 miles on the odometer. And what I wanted to mention here is all of these vehicles that were tested of the light-duty variety that we tested, none of them had been certified according to the unified cycle, but rather had been certified to the FTP. And because they were certified to the FTP, that's a much less aggressive drive cycle than the unified cycle. So these vehicles ought to be emitting more than under the FTP condition. But yet you'll see with this vehicle that had about 50,000 miles on the odometer, its emission rates were quite low, less than 2 grams per mile CO. These are second-by-second data. Hydrocarbon emissions, again, very, very low readings. NOx, quite low. And then we have PM measurements made by a nephelometer, which measures light scattering. And there is some question about what you're actually measuring under those high humidity conditions. Nevertheless, a nephelometer was used for light scattering. Finally, we have data collected for black carbon using the photoacoustic method. And this is a very good measurement for measuring black carbon specifically. And you can see that there are different periods when these pollutants are being emitted by this vehicle in the cold start, and then occasionally when this car would go off cycle under a rapid accel kind of condition. So you can see some small bursts of pollutants that correspond with one another. Here's the same vehicle now. What I've done is I've taken the cold phase and the warm phase and I've overlapped them with each other. And so what we see here is the red phase is the warm phase and the blue data is the cold phase. And where there is good overlap, you see that there's good reproducibility, and that is something that that vehicle consistently does. And then you can see whether or not it might be just a normal thing or an anomaly, or whether that's really happening. And again, you can see that most of the PM and the emissions are coming from the cold phase for this vehicle, with an occasional burst of pollutants that's coming from an off-cycle condition. And again, good reproducibility for the black carbon. So a point here that we see even for spark ignition vehicles that they are producing black carbon at various times. Here's the vehicle number 4 in our data set, about 50,000 miles again, not certified to the FTP. This vehicle here, a Jeep Cherokee, does not emit those bursts of CO or hydrocarbons at later phases during the unified cycle, but rather at the cold start. So that's where most of the emissions are coming from for those normal emitters. We have a kind of an anomalous burst here of reading for the PM measurements and then black carbon at different phases throughout this. If we overlap the cold and warm phase, you can see how reproducible some of these readings are, say for the black carbon, that's consistent. You see it happening both the warm and cold phase, so that's not a function of the cold start, where we do see it early on in the cold start. Now I'll show just a little bit of the air toxics data we collected. You are all well familiar with the EPA's list of mobile source air toxics, 21 species. In this study, the ones in orange and red we measured. We can't report data for acrolein and 1,3-butadiene because there's instability in the canisters for those species. But of those that are measured in red, we have the following data. These are scatter plots of total toxic emissions, sum of species versus CO. And when we do the regression plot, you see pretty good correlation between total toxics versus CO. When we eliminate the one high emitter and just use this part of the data, we get a much better correlation between total toxics and CO. For hydrocarbons, excellent correlation between the heated FID and sum of species. So one could recommend just using a heated FID, flame ionization detector, for toxics, as opposed to really getting into detailed chemistry because of the good correlation that you see here. This is the data set for the 28 vehicles for which we had speciation. When we eliminate the one high emitter, we still have very good correlation between those species. NOx, not so good comparison. And I'll conclude with my observations and implications slide. First, that of the sampled spark ignition vehicles that were in this, although the sample was weighted toward older, higher mileage vehicles, where we saw that the 10 highest emitters contributed about 2/3 of the CO, hydrocarbons, and PM, and about 40% of the NOx. Even among these older vehicles, there was skewness. So if we were to try to sample an on-road fleet where there are many more newer vehicles than older vehicles, the skewness would be even greater. Secondly, the 10 highest PM emitters were also significantly high for the other pollutants. So again, when a vehicle is broken, it's emitting a lot of all of the pollutants. For normal emitters, nearly all of the PM is from the cold start and some hard acceleration conditions. Number of high emitters and amount of and composition of emissions that they produce is absolutely critical, as you'll see from Eric's and Jamie's presentations. We also learned from this, and we've seen this in other studies, that normal emitting vehicles produce black carbon. And we see for toxics that you can do total hydrocarbons by a heated FID and get good agreement or good correlation between that and the GCMS, a more expensive method. We also see the cold phase PM are very important for normal emitters. So the amount of the cold start emissions is very important for normal emitters. And we've seen in our other studies where it gets down to colder ambient temperatures like you'd have here in Sacramento in the wintertime, you're going to have some significant PM from spark ignition that hasn't been well quantified yet. And again, the caveat that the source profiles that we've developed for this study shouldn't be used for other regions, even in California or wintertime, until it can be demonstrated that these profiles would be applicable in those studies. And the data right now are available at this website, and we've got them posted there, and so all the data and profiles are available, and people can access them. Because we're running just a few minutes over, we'll just go ahead and turn the time over to Jamie Schauer. Bart, do you want to introduce Jamie then? Well, I guess we can take time for a couple. I don't want to run over into more of their time. Thank you. There's one hand. Was there a question? Questions? Okay.
Okay, our next speaker is Professor Jamie Schauer, who's with the Environmental Chemistry and Technology at the University of Wisconsin-Madison. He came to us from Caltech. He's a former protege of Glenn Cass and certainly is promoting the multidisciplinary approach that Glenn took. Jamie seems like a young-looking guy, but quite a bit of experience, both in the private sector as well as a researcher with a focus on PM emissions. Jamie?
Thank you. What I'm going to do is I'm going to go ahead and sort of take off a little bit from where Doug left off, and I think Doug gave a good introduction to the study. What I'd like to do is sort of cover these topics here. First of all, I'd like to sort of talk about, sort of rephrase again some of the goals and objectives, what we wanted to sort of achieve in the study. And basically, the next 4 topics are basically 4 papers that we're submitting for publication that come out of the study, and I kind of want to highlight on these 4 different topics. Basically, the first thing is the sensitivity of the OC and EC emissions from the spark ignition or gasoline vehicles and the compressed ignition vehicles. This has important implications both for the molecular marker source apportionment work that we want to do, and also for those of you interested in black carbon as it relates to climate change issues. So trying to get a good fingerprint for what these different types of vehicles look like and what is causing, or what parameters in terms of driving cycle and vehicle conditions may be important to that. Then I'd like to talk a little bit about the sensitivity of the source apportionment profile as a function of these different fleets and driving conditions, again, from the different matrix that Doug mentioned about that. And as I'll highlight for both of the ECOC and also the molecular markers, is that we can talk about the variability among an individual vehicle, but we can also, which I want to focus on, is talking about the variability among sub-fleets of vehicles. Okay, there's a very big difference when we're talking about source apportionment, understanding the difference between the variability among the different two vehicles and the variability among sub-fleets of that. I'm also going to mention a little bit, as Doug mentioned, we did some testing over a 3-week period, and we basically did averaging across all the Sundays, Mondays, days of the week, and basically see how the source apportionment changed for this sort of relatively short time series about what the sources look like. I think people are familiar with the differences between weekday, weekend for mobile sources, but also some interesting things about other sources we see. And then finally, the last topic that I really want to focus on is how the sensitivity of these different source apportionment profiles, or the profiles that we got out of the study, affect what the CMB, or the source apportionment results that we want to have in the study. And then again, just close real quickly on sort of the implications of the study. So I guess sort of rephrasing in a different way, or me focusing is sort of the goals. I guess the two main goals that I see for this study is, one is to assess the accuracy of this chemical mass balance approach using molecular markers to quantify the impact of the primary gasoline spark ignition vehicles and the diesel combustion ignition vehicles to the atmospheric particle concentrations. And secondly, which I think is equally as important, is not just what the answer is, but determine what is the most important source of the uncertainty in this type of approach to understanding what the impact is. And I think that's important for us as we look at future studies or applications to other places to understand what are the greatest uncertainties and how we can reduce these uncertainties. Within these sort of higher level goals, I guess I also have some objectives that I think, and these are the things that we actually did, the tasks, and I just want to sort of summarize those. And one is to estimate the uncertainty in the ratio of elemental carbon and organic carbon to total carbon in the emissions from the Southern California summertime spark ignition and compression ignition fleets. Estimate the uncertainty in the average fingerprint for the source apportionment of the composition of that particulate matter emissions from the Southern California fleet. Assess the primary variables in impacting with this EC to total carbon and OC to total carbon ratios. So what is important about the fleet characteristics? This is important if we're trying to predict what things are like in other locations, or predict what future is going to be like, or also to understand if the fleet really is representative of what's out there. Likewise, the same thing about assessing the primary variables impacting these fingerprints or molecular markers to that fleet, and also to assess the impact of these uncertainties and our ability to do source apportionment with this type of tracer approach. So Doug gave a matrix of the vehicles that were tested. I just want to sort of summarize here. The numbers that I'm showing here are a little bit different with Doug presented. Doug presented the vehicles that we tested. What I'm showing here is the vehicles that actually have validated. There was a few tests that were invalid for some reason after the fact, or there was a few vehicles that were diluted so much that basically we were unable to measure things. And so basically we had 53 spark ignition gasoline vehicles that we tested. One of the things I want to point out is that 46 of these were recruited as non-smokers, and we deemed them as non-smokers. And I guess we should say that in some ways the distinction between smokers and non-smokers is somewhat arbitrary, but I'll show some figures in a minute which we can look at that. I also want to note that 2 of the vehicles that were presumed to be relatively normal cars were actually smokers, and so that's an important thing to make a note of. And that we also recruited 5 smoking vehicles. And all of these vehicles were tested in a 2-part cycle, as Doug mentioned, a hot unified driving cycle and a cold, and we collected samples in those separately. And as I'll say in a minute, we basically did bulk chemistry and every test individually, and these molecular marker analysis and composites. In terms of the compression ignition of the diesel, we had 34 vehicles. 2 of these were passenger cars. There was 7 Class 1, 7 Class 2, and 16 Class 3 vehicles and 2 transit buses. And as Doug indicated, these were tested over multiple cycles. And so we basically look at things basically as a function of the vehicle fleet class and also as a function of the cycle. So I'm not going to go too much into the chemical analysis methods. For those of you who are interested or not familiar, there's a lot of literature in this area, but I want to sort of emphasize a couple quick things about the analytical methods. Everything that I'm going to be talking about for organic and elemental carbon are based on what we call the NIOSH 5040 method or the Sunset Labs, or some people would call this the STN method. Erica is going to be talking about derived both the IMPROVE or the TOR method as well as the STN and what the implications are. So everything I'm saying is based upon this sort of definition of what elemental carbon is. And basically the molecular markers or tracers that we used were basically by GCS methods that have been published in the past. We collected mass data that DRI actually did from gravimetric analysis, sulfate, nitrate, and ammonium from all these things, as well as metals by XRF. And so these were used both for the source and ambient profiles. What I've shown here is sort of getting ahead a little bit is that this actually is a plot showing the elemental carbon to mass ratio as a function of the emission rate for the spark ignition vehicles. And you can see here in blue, this is the actual cold start for the cars, and the red is actually what's the hot start for the vehicles. So you can see here we're talking about a tremendous variability across vehicles. So we're talking about vehicles, as Doug mentioned, of a few hundred milligrams per kilometer is the units I'm using here, and also very large differences in the EC to mass ratio. You can see at the low levels that we expect, there's relatively high uncertainty. But one of the things that I think I want to emphasize, and that's sort of as we construct profiles for doing source apportionment or trying to get estimates of what the fleet is like out there, it's not necessarily what's important about the variability between vehicle to vehicle, but it's how aggregates of these vehicles vary among each other. And so one of the exercises that we did with this data is we actually did a lot of different types of averaging of this fleet and breaking them up by different types of categories and seeing how sensitive it was to different effects of what the fleet is. And so basically we looked at, what I've only shown here is some of the cases, but we looked at the actual test cases. We looked at only cold start, only hot start. We got from ARB, Doug I think got from Hector Maldonado, basically the MFAC estimates of what's actually on the road, and we were able to take our fleet and then scale things up to what we expect to be on the road. And what you can see here is I'm presenting the actual averages of this EC to mass. The top part here is basically what I call the base case or most realistic cases, and basically again, all the data points are shown, the actual individual tests, and then this is the solid line here is the tested vehicles, the actual ones that were tested, the average for cold start, the warm start, and basically what we consider to be our LA distribution with 5% smokers for the hot and cold and 25% smokers. And again, these are not necessarily mean to represent this is what I think the average is, but to cause different bands to understand the sensitivity of how we average these things together. And one of the things that's important to recognize is that within these base cases, actually the ratio of this EC to mass is relatively stable, so it's insensitive to how we average these things up. If we look, we also have what we call the higher meta cases. We're actually considering unrealistic conditions about there being 50% of the cars are smokers or 75%, which is very high, just to see if you were in a microenvironment what that effect would be. And we also looked at cases where we could assume that there's only new cars. And this is how we've come up with a sensitivity of what we think the best estimate of the fleet would be. And again, we're saying that of all the vehicles we tested, we think that they're representative of their age category on the road. If the vehicles we tested are not representative, there's not much we can do. But giving this data, there's different ways we can say what their relative distribution would be like out on the road. One of the things that I wanted to show here is actually of these different categories, which these averages are sort of also reflected in, you can see here that this is the mass emission rate of the averages, not necessarily all of them now, but based on the age classes, when cold, warm, and cold, of the cold and warm sets. And what you can see here is that even across all these different age differences, the ratio of EC to OC and mass actually isn't that variable. But what I've shown over here is the 7 smoking vehicles, 5 that were recruited as smokers and 2 that weren't, about what their mass emission rate looks like and also what their EC to OC ratio. And one of the things that's very staggering about this is the variability among these is phenomenal. I mean, basically you're talking about vehicle 5 here, which is basically all organic carbon with relatively high emissions. You're talking about vehicle number 6 in the warm start and 7, which very high amounts of EC to OC ratio, so almost all EC, and moderate emissions. And so there's a whole different spectrum of what these are. And one of the key points I'm going to get at is we're going to need to do a better job in the future of understanding about these smokers. I'm arguing here and we'll show more, is that I think that for normal emitting vehicles, we've done a pretty good job characterizing those, but for these smokers, we really don't understand them very well. And that's something that's going to be very important in the future of understanding what the average of a smoker looks like. And I'll get to that more in a little bit. What's shown here actually is the molecular marker profiles of that sort of the similar theme. And I know we were talking earlier, Bart, before about the different types of smokers, and this sort of plot helps us figure some of this out. I'm not going to get too much into detail about that, but basically saying is that as we start constructing averages across the SI vehicles, we come up with relatively stable amounts of these profiles. But if we start looking at the smokers, because of the tremendous variability and the low number of vehicles that we tested, it's very hard to say what the average of that looks like. What I've shown here is basically these hopanes and steranes. I should use my pointer up here, which are basically things that we use as molecular markers. Also pHs, which have been shown to be very important, from these spark ignitions to high molecular weight ones. And again, these are the important tracers that are associated with mobile sources. I've done a similar thing for this compression ignition or the diesel vehicles, which you can see here is actually shown in green is the actual data points of the different diesels on different driving cycles. But I've also here, just for a reference point, I've also included here black, which is actually the idle of the diesel test. And obviously, the x-axis here is different. This is showing the mass emission rate, and obviously it's idling. The mass emission rate is infinite because it's not going anywhere. And so basically, what that really is the concentration. But the idea of putting it here is to give you a reference of what the EC to mass is. And what you'll see is that the EC level of these is much, much higher. And there's also quite a bit of variability in terms of emission rate and across different, the ratio that the concentrations are. Again, we've constructed similar types of averaging where we can segregate these out based on vehicle class, also by vehicle age and also driving cycle. I don't show vehicle age here for simplicity, but one of the things, again, that's interesting if you look across the vehicle class, what you'll find is there's not a lot of variability when you average across these, but the strongest parameter that's affecting what these averages are is actually the driving cycle. And for the people who've studied driving cycle second by second for diesel, you'll know that the driving cycle is very important to what that average composition is. Another way of showing this is basically similar to the plot I showed before about the mass and the ECOC. What you can see is people always say that, you know, the age of a diesel vehicle and also the size of it is very important to the mass emission rate. And you can see those both here in these two trends that I show here. But if you look at the composition of it, what you see is that it's relatively stable across age and class, but is much, much more sensitive to what the driving cycle is. Okay, and there's lots of sort of fundamental studies of diesel engines that have kind of shown the same thing. So again, one of the important points of this is that we need to make sure that we have a good match of what the diesel driving cycle is, and we think we have a good average of that for the study, but we'll look at a sensitivity in cases where that would be wrong. The same kind of plot I can show for the molecular markers. One of the things that's really interesting about the data from this study, which is different than some of the data that I've seen from 20 years ago, is that the fraction of EC for these diesel vehicles, as I said, is really much approaching 1. It's almost all elemental carbon for these. And in that case, these molecular markers become relatively not that important because their relative contribution and how they do in terms of the model and the atmosphere is relatively small compared to the spark ignition vehicle. Nonetheless, we can do the same kind of averaging and sort of see that the sensitivity of this is not that great across the different vehicles. Once again, these are normalized to organic carbon, not in terms of actual mass emission rate. So we're trying to get a fingerprint. So some real sort of quick conclusions about the uncertainty of the profiles before I move ahead. I think that for the non-smoking gasoline vehicles, the composition of the average PM emissions are reasonably stable as a function of the fleet mixture for the different type of sensitivity that we're looking at. For smoking vehicles, there's considerable variability among the different smokers, and therefore, from the data we have, it's pretty hard to estimate what is a good estimate of what a smoker's average profile is, and I think that's an important thing for the future. Likewise, I think for the driving cycle is the predominant factor affecting the average composition of the PM from the diesel vehicles. So that's important, again, as we look forward to predicting what things are like or making sure that we have the right matching, as Doug said, about validating how these profiles could be used in other locations. So what I want to talk about next is actually the CMB sensitivity. And so in this chemical mass balance, basically what we're using is all these different profiles we've come up from the different fleet averaging. And there's sort of 4 different categories I want to sort of look at. One is what I call sort of the base case model, where we're using our average CI and average SI profile. The average CI averages across all the vehicles we tested. The average SI is using the LA distribution with somewhere between 0 and 5% smokers, which again gives us a very stable profile. And using what I call my sort of proverbial oil burning smoker. And I guess prior to the work we've done before, this is sort of what we classified as a traditional smoker. And I think one of the outcomes of the study is that there's a lot of different types of smokers. But basically, looking at this as a base case, and we're going to look at how this affects day of the week, and then looking at a sensitivity to the average SI profile. So looking at, of all the different ways we constructed the SI profile, or the gasoline profile, how that changes the source apportionment answer, and we're going to look over across a very wide range. Look at the sensitivity across the diesel profile, so looking at the different ways we can average these up by driving cycle, by age, and different things to see how the profile changes. And then finally, at the last, look at the sensitivity to the smoker. And basically, the idea being is that there's a lot of variability in the composition of the smoker, and what does that mean for the source apportionment results? So real quick, I just wanted to show a little bit of the data about the day of the week analysis, and I don't want to get into this too much. We've sort of written up a whole paper about this, but basically what you can see plotted here is the OCEC sulfate nitrate, ammonium, and the mass composition of for the two different sites that Doug highlighted, Azusa, Los Angeles. This is the day of the week. Basically, this shows the OC and EC concentrations, and you can see some of the trends that have been observed before, so I don't really want to dwell on that. But what's shown here, basically, is the apportionment, not of the mass of particulate matter, but the apportionment of the organic carbon and the apportionment of the elemental carbon for the two different sites using the base case as a function of the day of the week. And some of the things that you'll see first, as Doug alluded to before, there's a lot of this other, and this other means that sources that we don't have in the model plus secondary organic aerosol is being formed. You can see here some trends in what the EC, the CI contributions was shown here in black. You can also see some trends in the meat and also in the wood burning, which is actually pretty small, which you don't see here very well, but there is actually a pretty strong weekly pattern. Another thing that's interesting to look at is that when we apportion it for where the EC is coming from, we see a predominant amount of the EC is coming from diesel, okay? And again, Eric will talk about this more later. If we were using a different measure of EC or a different definition of EC, we would not necessarily conclude the same thing about the sources of EC. So what I wanted to show real quick was basically the sensitivity to the SI profile for the different gasoline vehicles. And what basically, probably you can't read that in the back, but basically what's shown here is this condition where we have only new vehicles. We have this 5% smoker with the LA distribution, the 25% smoker with the LA distribution, only using cold, only using warm. And basically what we find is that the source apportionment results are relatively stable. So in other words, however we construct that SI profile, there really isn't a big difference across all the different vehicles we tested. And so therefore, one of the conclusions is that it is relatively stable, that we have a good, what I consider a good capture of what that vehicle is, of the average of the SI vehicle. And likewise, that our ability to understand about what that average is, I think, is relatively stable. We've also done a similar thing for the CI profile, and what you can see here, again, I guess I should have said real quick up here that on top, again, is the organic carbon and the elemental carbons, understanding about where those are coming from. So here, again, with the SI profile, we have also, did I just flip? Okay, the sensitivity to this profile, this is for the Tuesday, this is for Saturday. We see here for the LA site a little bit of these extreme cases, the 25% smokers, which again, we don't believe there's really 25% smokers out there. We start seeing things that aren't as stable, but across sort of the base cases, we see things that are pretty stable across there. Likewise, for the CI profile, we've done this where we're actually looking at using only the pre-1990, the 1990-93, the 94 to 97, or the 98 to 2001, only using this cycle, the different cycles. And again, we see that the contributions to the source apportionment, again, are pretty stable. We see some slight trend in here and with the diesel contribution for organic, but again, across the wide range of these, I would say that the results, again, are pretty stable. And we don't see very large differences in what the apportionment would be. Same thing for the Saturday case. Again, we do see some trends, but we don't see things changing that much, so we have a relatively high confidence in the model. Again, I want to go back again and talk a little bit about the smokers, because what I want to highlight or end up with is basically the statement about our analysis of what the sensitivity of the smokers are. And I want to highlight again here about how we see the non-smokers having relatively stable profiles, but as we move across these, we'll see, I'm going to show on a plot in a minute, the smokers that we're going to focus on is the smoker 4, 6, and 7. So that's basically the smoker in here, number 4, which has very high PM emissions and has a moderate amounts of EC. Number 5, which is the one that has very low EC but still high emissions, and 7, which is one that has very high EC as well and the high emissions. And I'm not going to, I'll show in a little bit with the molecular marker profiles, but again, these are very different types of profiles, which you can see. And again, I want to emphasize that the variability of these is much, much, much greater than we see for the average profiles that are shown for the average or sort of normal or typical vehicles. And again, this is the spark ignition profiles here again for vehicle 7. We can see here the 4 and the 5 are the ones with these different molecular markers. We're seeing higher hopanes and steranes here than we do, and again, that's all indicative in the profile, which I don't want to spend too much time talking about the details of these differences. I think it's interesting to note that these differences can be related to the mechanisms of why the vehicle is smoking. So again, some of these indicate there's burning oil and there's lubricating oil. Some of them talk about a lot of pyrolysis being in the engine, the pHs and the EC, and so I think there's some additional things in here, but sort of beyond the scope of what I want to talk about today. So what's shown here, this is kind of a busy slide, but what I wanted to show is basically what the implications of these different smokers are to the source apportionment result. And what's shown here is basically the gasoline vehicle, which is the SI plus the smoking vehicles and the diesel. And basically what this is shown across the 4 days of interest, the Azusa Saturday average, the Azusa Tuesday average, the Los Angeles Saturday, and the Los Angeles Tuesday, and basically what the contribution to OC is. And one of the things that we found is that with the variability of this smoker profile, the model actually had a lot of collinearities in it. So basically the profile of these smokers were too similar to the diesel and too similar to the spark ignition on average. In other words, it really covered the full spectrum of things. And so what we did is sort of through brute force, we came up with an average SI profile where we averaged the smoker with the regular different fractions, 10, 25, 50, 70, 95%, and basically ran the case for all of these. And basically the sort of the summary here is that under some conditions, things are relatively stable, but under many conditions, the model was completely variable. And so basically the sort of the take-home message of this is that for the smokers, we really need to know ahead of time or do more testing in the future about what those smokers are really like to be able to do this apportionment. Okay? So as the information we have now, I'd say that we don't know enough about the smokers to very accurately say what their impact is relative from the source apportionment approach. If we a priori said this is what we believe a smoker to be, then we would be able to, the model would be very stable. But the data from this study suggests that we cannot do that. So a couple of sort of conclusions about the sensitivity analysis. The CMB model is relatively stable for all cases for non-mobile sources. So if you look at all the different cases, which I didn't show, about the wood smoke and meat smoke and road dust, things are relatively stable across all these different sensitivity analyses. The largest uncertainty for the gasoline-diesel split is associated with the uncertainty of the smoker profile. So what do these smokers look like? I didn't do a lot of showing this here, but basically the sort of the no smoker scenario is not a good fit for the CMB model. If we basically force the model and take out the smoker, we basically don't get a good fit by sort of the average vehicle and what the diesel is. That's not a good combination of that. And I guess the point being is, given a constraint on the composition of the average smoker, the CMB model is relatively stable, but in the absence of that, the model can sort of be all over the place. The implications of this is that I think the molecular marker CMB models do a good job with non-mobile source apportionment. The composition of the average CI fleet emissions is very sensitive to the driving cycle. The composition of the SI fleet emissions are very sensitive to what the smokers are doing. In the LA basin, the EC emissions appear to be dominated by the CI engines. We also need better information on the average composition of the smoking gasoline vehicles to improve the accuracy or the faith that we have in the CMB models. And then I guess finally I would say that sort of additional sort of comments about the implications is that I think in the LA basin the reduction of the EC emissions needs to focus on CI. Again, if you're using the definition of E that I'm talking about of EC, the smoking vehicles are important contributors to the total OC emissions of mobile sources. Again, this sort of idea that if we had preconceived constraints about what smokers are, we could have a lot of stability in the model, but this study raises a lot of questions about sort of what that sort of future or what the average smoker is out there. And finally, I just want to sort of conclude with some acknowledgments, the funding that Doug had mentioned and the people that have played a part in this from the other institutions as well as from my group as well.
Okay, our last speaker is Professor Eric Fujita. He's with the Desert Research Institute in Reno, Nevada. And while Eric was an employee here at ARB and a doctorate student at UCLA, he did seminal research on comparing ambient data to the emission inventory. And at DRI, he's greatly improved on this top-down emission inventory reconciliation to the advanced hydrocarbon and PM source apportionment that he'll present here.
Thanks, Bart. I want to first acknowledge the colleagues at DRI that participated in this study. As Doug said, the objective of this project was to determine the uncertainty in doing a source attribution of gasoline and diesel emissions in an urban area like the South Coast Air Basin. And there's many sources of uncertainties and variation in the split between CI and SI apportionment. And I've listed here some of the main factors that could account for this variability and uncertainty. First, there's emission characterization. There's variability in the abundances of various marker compounds for normal versus high emitters, as Jamie has discussed. The test cycle that's used to collect these samples have a lot to do with the relative compositions of exhaust, especially EC and OC, as Doug pointed out. There's the ambient measurements. There's a lot of variability in the spatial variation and temporal variation of PM emissions, both diurnally and by weekday. And also there are seasonal differences related to temperatures. There's also atmospheric transformations that have to be accounted for. As far as measurement methods, the sampling methods have a lot to do with the amount of material collected on the sample and the split between the more volatile species, semi-volatile species, and particulate species. Analytical methods, in particular, the carbon method, is very important in determining how much OC and EC we see in the sample. And that has important implications for doing the source attribution. In the application of the CMB model, there's various decisions that an analyst would have to make. That is, how would you composite all of the various samples that are collected into composite samples? Which of these composite samples do you use in the source attribution? What fitting species should you use? And finally, and often overlooked, is how you present the results. Have a lot to do with the impression people get. So I'm going to start with the distribution of carbon, of the various carbon fractions in the composite profiles that we develop. On the left panel here are the diesel. There's the heavy composite of the city-suburban cycle and the highway cycle, and then the individual composite profiles. Also, I have here the composites of the light-heavy and the medium-heavy duty trucks. And for the spark ignition vehicles, we've developed 6 composite profiles. 3 of them are the cold start, the other 3 are warm start. And for each of these, we have a composite of the low emitters, the high emitters, and then several vehicles that had higher amounts of black carbon that really didn't fit with the other vehicles. See that for the heavy-duty exhaust, there's much more elemental carbon than we would find in a typical gasoline profile. And most of the EC is in the EC2 fraction versus the EC1. Let's see, we'll go to the next one. As Doug said, most of the emissions come from a certain part of the cycle. What I've shown here is 4 different vehicles. A very clean vehicle is shown in green. And you see, as Doug has shown, most of the emissions come during the hard accelerations. The common emitter has more emissions, but generally the same pattern, although you see some emissions during more mild accelerations. The red is a smoker, And you see that the cumulative emissions are more linear with time, and it's emitting black carbon all of the time. And the black is the light-duty diesel vehicle, which emits black carbon all of the time. So you see a tremendous range in black carbon emission rates. You see that the low emitter, even the hard acceleration, its emissions is 4 orders of magnitude less than a typical diesel light-duty vehicle. So the question that would come to mind is, what effect does the test cycle have on the amount of elemental carbon that you see in the exhaust for spark ignition? And that's a relevant question. I wanted to go over this map that shows the various sampling sites. What I'm going to talk about in the rest of my presentation is the 3 fixed sites, LA North Main, Azusa, and San Dimas. San Dimas, this particular site was located in a regional park. It doesn't have any influence from local traffic, so it's what I would consider more regionally representative than someplace like LA North Main. The other samples that I'm going to talk about, Doug mentioned that we collected various other samples that represent different mix of diesel and gasoline traffic. The one that there's 4 samples that I'll show later on in the apportionment. One was collected not at Dodger Stadium, but the Rose Bowl after a soccer game in Pasadena. The other was a sample that we collected along the 405 on a weekend, going back and forth from Westwood to San Fernando Valley. The interest in that particular sample was what effect does load on the vehicle have on the composition of that vehicle and emissions. We also had a sampling site in Venice during a weekend, and at that particular site, it's kind of a background site. Does not have appreciable amount of diesel traffic. The other sample was from the Terminal Island area, heavily diesel dominated. I could show many of these types of graphs that show the different locations where we collected samples. What this graph shows is the PM estimated by the dust track measurement. This is a measure of light scattering. And the photoacoustic black carbon, which actually measures light absorption. And you see the BC scale on the left scale, and this particular sample is taken after the soccer game at the Rose Bowl. And the sampling began just before the cars began to leave the parking lot. So you see the emissions starting out, the concentrations of PM starting out here. See a rise as the vehicles began to leave, and a gradual rise until all the cars cleared the area, and then we took the sampling van away from that area, and we're back in the urban background again. During this entire time, you see that black carbon was basically in the urban background, little less than 1 microgram cubic meter, which is typically the background concentrations in LA. So you see that despite the fact that there were thousands of vehicles traveling near our sampling site, we didn't measure much black carbon, which shows that gets back to the point that the driving cycles do matter. This shows the freeway sample during mid-morning in the central part of the basin where there's a lot of trucks. This is the 710, the 91, and 605. So you see that in this case there's a very good correlation between light scattering and light absorption. You see the correlation here. And you see that in this case the black carbon concentration is significantly higher than in the previous slide that you saw from the Rose Bowl. Here you see a peak black carbon concentrations of about 60, 70 micrograms per cubic meter. In fact, there's one program that not this particular study, but we made similar measurements in this location and measured 300 micrograms cubic meter of black carbon. This shows the carbon fraction distribution for the samples from Azusa and from LA North Main for a day of the week, and also some of the samples collected from the mobile sampler. You see, these two are freeway samples collected on Sunday, freeway samples collected midweek, one in the western part of the basin, another in the mid-basin where there's more trucks, Terminal Island and a truck stop. There's Cajon Pass and a couple of Surface Street, the 405 sample from Westwood to San Fernando Valley, and the Rose Bowl sample. See, in these samples, there seems to be much more E2 than in the monitoring site at either Azusa or LA North Main. I'll talk a little bit about the comparison between the STN and improved carbon data. There's been a lot of discussion about that recently, but one of the objectives of our study was to look at the effect of using either STN carbon data or improved carbon data to do the apportionment and see if the results are appreciably different. What I've shown here is the elemental carbon concentrations for heavy-duty diesel testing, and the upper left shows all of the data. The lower left shows a smaller portion of that graph near the origin. And you see that for all concentration levels, there's very good agreement between STN and improved carbon data for EC, total EC. The right two graphs shows the same data for light-duty gasoline vehicles. And you see that if you plot all of the data, with the exception of this one outlier, there seems to be fairly good agreement between the two methods. The slope is near 1, and there's pretty good correlation. But if you look at the lightly loaded samples, or for the cleaner gasoline vehicles, you begin to see divergence between the two, with improved measuring higher elemental carbon concentrations. Now, if we also look at ambient samples, this is from the various ambient samples, both fixed site and mobile, and plot the STN versus improved. And you see that there's a offset. The slope is about 0.7 between the two measurements. So those differences do show up in the result for source attribution. If you were to do the source apportionment, and in this exercise we just use a default set of profiles for gasoline, diesel, and did the data using either STN or improved for both the source and ambient data. And what's plotted here is the source attribution in micrograms per cubic meter of total carbon for diesel exhaust. And you see for diesel exhaust, there's the same sort of offset that we saw in the ambient data of about 0.7 slope. For a gasoline vehicle, doesn't seem to matter a whole lot. You see that this is the one-to-one line down here, and you see that the carbon method didn't have a whole lot of effect on the attribution of gasoline vehicles. Now, if you took EC out of the fit and did the source attribution using only organic species, and we didn't use metals either, just organic species, PAHs and hopanes and stearates, you see that removing EC then gives you very different answers with and without EC in the fit for compression ignition exhaust contribution. But for spark ignition, the results were similar with or without EC, which means that the organic compounds have a more controlling effect on the apportionment for gasoline vehicles, and that the diesel exhaust contribution really dependent on what the EC concentrations were. I'm going to show a few slides showing the composition for PAHs, hopanes, and stearines for the gasoline and diesel exhaust. Again, the left is the heavy-duty diesel trucks, the same four groups, and the same for light-duty gasoline categories. And you see that there is a significant difference in the composition between gasoline and diesel for the higher-end PAHs. See, chlorine, benzoyltripyrrolene, and denylpyrene are a significant part of the light-duty gasoline exhaust. It doesn't show up at all in the heavy-duty diesel exhaust. Now, if you look at the composition of PAHs, those same PAHs in the fuel oil for diesel fuel, the lube oil in diesel vehicles, and the lube oil in spark ignition vehicles, you see that for gasoline vehicles, the composition of these PAHs are very similar in all of these used the lubrication oils. And you see that even the low or the newer vehicles, the lower emitters, have very similar composition to even the smoker category, the S10. There's some of the PAHs in the compression ignition lube oil, but there's concentration expressed in terms of microgram of these PAHs per gram of oil. It's much less in diesel lube oil and significantly less in diesel fuel. Now, I slipped one slide in here that was not in the presentation that was posted on the web. I wanted to show this because I wanted to show the significance of the volatile PAHs relative to the particular PAHs that I was talking about in the previous slides. This is actually, this data is from the Kansas City Vehicle Characterization Study, which was conducted last year and this year for EPA. Still an ongoing study, but I did present this slide at the 15th CRC on-road vehicle emission workshop this spring, so I guess I'm free to show this here. Well, what's plotted here is the 3 PAHs that the potential marker species for gasoline vehicles, and also the 26 other particulate PAHs in gray, and then also the 63 volatile and semi-volatile PAHs. This is the sum of 63 of these compounds, and also the most volatile PAHs, the naphthalene, 1 and 2 methyl naphthalene. And you see it in the 100% plot that most of the PAHs are the volatile PAHs. You see naphthalene, 2 methyl naphthalene, and 1 methyl naphthalene make up almost 75% of the total PAHs. So this is a very significant source of these light PAHs. I know there's some interest in the emissions of naphthalene these days. So I wanted to show this to reinforce the significance of light-duty gasoline engines as a source of these volatile PAHs. Now I'm going to go to steranes, and this is the sterane composition in lubrication oil. And you see remarkable similarity between the sterane composition in all of the lube oils. For low emitter composite, high emitter composite, the black smoker composite, and also the 2 compression ignition composite. The relative abundances of these steranes are very similar. But on a concentration basis in microgram per gram of these steranes, you see that there's similarity between the diesel and the low emitter spark ignition. And you see that the higher emitters have significantly higher concentrations of steranes than the other 3. Now that was in the lube oil. If you look at the exhaust profile, you see that there is a similarity between these 2 high emitters, and the relative emission rates of these steranes in the high emitters are significantly greater, as you would expect, than the normal emitters. But what's interesting is that there appears to be a difference in relative abundance of the higher molecular weight steranes in spark ignition versus compression ignition. And you'll see that the same thing appears for hopanes. This shows the hopane composition in lubrication oil. You see, again, very similar composition. This says sterane, but this should say hopanes. You see very similar composition for the spark ignition and compression ignition. And again, you see that the relative abundance of these hopanes are higher in the higher emitter than the normal emitter or the diesel. And again, for the exhaust composition, see that there appears to be an enrichment. I don't know if that's the right word, but there's more higher molecular weight hopanes in spark ignition exhaust than in compression ignition exhaust. And again, the higher emitters have a much higher abundance of these hopanes than the normal emitters, and the low emitters have hardly any. So what result did we get? This is for the improved data, and what's shown here is the attribution of total carbon for diesel, gasoline, and the residual is not accounted for by either diesel or gasoline. See that for total carbon, diesel is the predominant source at LA and Azusa. But what's interesting is that for the other sites with more, or what we would expect, a higher contribution of gasoline vehicles, you do see predominantly gasoline contribution, like the Rose Bowl. Using improved data, you get about 2/3 for gasoline. In the case of STN, it's all gasoline. Similar thing for Venice, the 405, mostly gasoline for STN data, a little bit more for diesel in the case of that particular sample. At the San Dimas site, which we would consider more regionally representative, you get approximately equal contribution of gasoline and diesel. This shows the same sort of contribution estimates for elemental carbon. And as Jamie showed, it's predominantly diesel that is the source of elemental carbon. About 90% using STN data, well, 90 to 95% using either STN or improved. And organic carbon, here predominantly residual carbon not accounted for by diesel or gasoline. And we did not apportion to the other potential sources of organic carbon, like meat cooking or wood combustion. But in our case, we see more attribution for diesel than gasoline. That's at the 2 monitoring site, but of course, the other sites where we expect more contribution from gasoline, we do see a contribution, predominantly contribution from gasoline. We did a comparison of the 2 measurement methods. This is a quantitative comparison between the improved and STN approaches. What you see for total carbon is that by using improved, the average, this is an average of all the Azusa and LA weekday samples. You get about 41% contribution to compression ignition if you use just improved for both source data and ambient data. If you use STN, it drops to 31%. If you use STN data with no PAHs in the FIT, it's very similar. But for spark ignition, you see that there's an increase from 7 to about 9.4 going from improved to STN, and then a slight increase if you remove PAHs. So the difference here in the ratios, you can go from a ratio of 41 to 6 in the case of improved to 31 to 9 STN and 31 to 11. So you get you get differences in ratio by using different methods and approaches. OC, same sort of thing. You get a reduction in OC going from improved to STN, increase if you use STN, and further increase if you remove PAHs from the FIT. Now the interesting thing with removing PAHs is it can't account for all the EC with the 2 sources. But if you use PAHs and either improve or STN, like I said, 90 to 95% of the attribution is to diesel exhaust. We're also interested in looking at the variability in the source attribution depending on what particular profile you use. And this shows the sensitivity of the attribution to total carbon using different gasoline profiles. And what's shown on the very left is the 6 composite profiles. And within those composite profiles, we show the individual profiles that made up the composite within that group and the variability. So you see that there is large variability within each of these composites, but if you look at the various composite, there's not much variability between the composite samples, at least for Azusa. There's more variability for LA, and in fact, much more variability for specific profiles. Same sort of sensitivity for CI exhaust profiles, the composites versus the individual. And you see ranges from 30 to 50, 60. So the individual profiles do affect what specific attribution you would get from the analysis. So I'm going to end with one summary slide and then 2 implication slides. So the factors affecting the apportionment for the split between gasoline and diesel, we see 4 broad areas of factors that affect this apportionment. One is CI apportionments are mainly dependent on EC, and the CI contributions were greatest with IMPROVE. The SI apportionment were most sensitive to PAHs, the 3 high molecular weight PAHs that we showed. And also the stearanes and hopanes have quite a bit of effect on the apportionment as well. But EC has little effect on the spark ignition apportionment. EC emissions for spark ignition vehicles were minimal except in cold start and hard act cells. So there's some issue about what sort of profile you should use for a particular ambient sample that you're looking at. Marker PAHs were present in used engine lubrication oil in similar proportions, but their concentrations tended to increase with the age of the oil. So the explanation there is the PAHs created during the combustion process. There could be some blow-by through the piston. These blow-by emissions go into the crankcase, and so the PAHs can end up in the crankcase. And over time, as the oil ages, can accumulate some of these PAHs. So that's another factor in this apportionment or the profile development is what is the age of the oil. One thing that we didn't do is look at the pH concentration for a clean, unused oil, but I suspect the concentrations will be very low. Most of the SI apportionment was associated with high emitter profile, so what we did in our apportionment was allow the CMB to select from these 6 profiles that we had, and generally it picked a high emitter profile. But as you saw, the apportionment varies with the specific profile that you use. And removing pH from the FIT increases the spark ignition contribution relative to CI. The CI SI apportionment does vary by location and time. It's kind of intuitive, I guess. The CI vehicles were dominant source of EC and TC at Azusa and LA North Main. It's more equal at locations that are more regionally representative, like the San Dimas site. And in areas where we expect mostly gasoline vehicles, we do indeed see predominantly gasoline apportionment. We also looked at alternative methods for deriving composite profiles. There's different ways to averaging by weight fraction or averaging by emission rates. One will weight the high emitters. The other approach will weight all of the profiles equally. And so we looked at the differences in that, and there wasn't much of an effect. So the implication. The emission of black carbon and PM were low for most gasoline vehicles, except in cold start and during hard acceleration. So the implication is what are the effects of the test cycle, and how does that translate into developing emission inventories of black carbon or PM for that matter. CI vehicles were the dominant source of EC. EC then is a reasonable surrogate for PM from CI vehicles in a place like the South Coast Air Basin. we estimate, and Jamie's analysis also is similar, that 90-95% of the total EC in the basin can be attributed to diesel vehicles. A large fraction of SI source contribution to OC was attributed to high emitters. The implication there is the existing controls do not adequately address these high-emitting on-road vehicles. The spatial and temporal variation in relative CI-SI apportionments were large, so therefore you must consider the purpose of the monitoring data. Are we looking at compliance with existing ambient air quality standards, or are we looking to reconcile emission inventory with ambient data, or are we looking to characterize exposure? So there are different purposes, and you need to be aware of those differences. PM concentrations of exposure were higher on and adjacent to major roadways and with high volume of diesel truck traffic. Seems kind of obvious. But exposures were also higher when following high-emitting gasoline vehicles. Found that not only in this project, but in other studies that we've done on exposure. And I'm sure Dane and Scott, who've done similar work for ARB, could have similar tales to tell. The implication there is the existing monitoring programs do not account for these higher exposures. Motor vehicles were significant contributors to semi-volatile organics, and these compounds are not currently routinely measured. Significant fraction of the organic carbon during summer in South Coast Air Basin cannot be apportioned to either gasoline or diesel. Jamie showed that some of it can be attributed to meat cooking and some to wood burning, but there's still a large residual organic carbon that's not assigned. So the obvious question is, what are the relative contribution of spark ignition and compression ignition to these unaccounted for organic carbon, and what is their role in formation of secondary organic aerosols? And same acknowledgement as the other two speakers. Thank you.
You saw a lot of variability, obviously, amongst the smoking vehicles, and I was wondering whether there was anything that you found about the characteristics of the vehicles themselves in terms of age or mileage that would eventually help the ability to develop some sort of weighting factor of those smokers into a fleet average. We need to do more work.
There needs to be more work, Karen. What we've seen in all of our studies where we've actually recruited or pulled over high emitters was that probably the only characteristic that is inherently similar among all of them is lack of maintenance. When vehicles are well maintained, irrespective, even if they're old, they're relatively low emitters. With PM, though, it may be a little bit different issue, because there the vehicle is just kind of aging and the engine is wearing out slowly and gradually. So with these new studies with PM, we're not as certain about some of that, other than the fact that what we did see was the emissions, when these vehicles tended to be high in one, they were high in all of them from this data set. But again, it's a matter of recruitment and understanding a little bit of that. And Jamie and Eric may want to try to answer that too, or add to that.
Thank you. In looking at the chemistry of this, it suggests to me that there might be an experiment to be done with a research engine in which you vary either the compression tightness or the combustion efficiency and see which way it pushes the chemistry of your effluent. It seems to me as though malmaintenance and tampering might result in things like excess fueling and bad spark timing, and those things might lead to one set of failure modes, and then obviously the loss of compression would lead to a different kind of failure mode, and it might might be useful to explore the chemistry of those two directions.
I can just comment real quickly. In terms of, at least to my knowledge, for this compression ignition diesel, a lot of that work has been done where people have taken these steady state engines and looked at how load and how, changing in timing and sort of failure things. But I'm not aware of anything with spark ignition. I think the challenge goes back to sort of Karen's question is that, there's so many different types of vehicles and, there's different types of failure modes. But I agree that, to get insight into that, it's clear that from the diesel side, there's a lot of insight that people have gained by looking at these sort of research engines and looking at how things fail and what's going on to understand that.
We have one question that was sent in or emailed in. That the first question reads, what are the DOE NREL plans to address the need for improved characterization of smokers in the fleet? Answer to that one is we're not quite sure yet. Depends on, I think, what we get from this study as well as what we get from the E55 and E59 projects that ARB is involved with on the heavy-duty side to understand, I think, in that case, how important high emitters are in the diesel part of the fleet. So I don't have a good answer to that one. Second question is, what are your thoughts regarding the future distribution of smokers in the fleet and their impact? That's dangerous to predict the future. Casey Stengel or Yogi Berra, and I'm not sure which one it was because I've looked on the web and it's the same quote is attributed to both of them, but the quote is, forecasting is difficult, especially when it involves the future.
I had a question. Doug, you observed pretty high correlations between CO and hydrocarbons and PM. So presumably the smog check program is at least capturing high PM emitters. Whether or not the repairs to address the CO and hydrocarbon readings are having an effect on a PM, I guess is still an open issue. And I guess the question for the group is, I know you have ambient data that's been collected in the 80s and 90s. Has anyone applied these same profiles to that earlier data, this new data you have regarding smoking vehicles to see if the trend for PM is up or down or the same for gasoline vehicles?
The answer is we haven't done that yet, but I also think that, between data that goes back 20 years and some of the stuff you're referring to is that old now. I think some of the profiles have evolved. I'm not sure that the old profiles have done a good capturing that, but clearly there's been an evolution in emissions. And so I think just as it's dangerous, it's probably a good exercise to see what the answer would be, but I think that I don't think we should try to use these profiles as a good representation of what, because it's a larger data set, more representative, as a necessary good representation to the past. So I think it's worth doing, but I think we need to be careful in how we interpret that.
Any other questions? Can you wait for the...
My name is Yin Su with Peckin and Associates. I've done quite a bit of speciation profile, that kind of things, for both ARB and EPA. So I've been looking at the ECOC and PM emission rate and speciation profile, that kind of things. I saw Professor Shaw, you just show a very interesting chart, or many charts, that you were comparing the EC fractions or EC to OC ratios versus the PM emission rate. I did this kind of analysis as well. On top of that, I also found, using the same set of data, but I saw different relationship was when I plot the EC emission rate versus PM emission rate, and also OC emission rate versus PM emission rate. So I saw very good relationship when I plot the emission rate instead of ratios or fractions. So I don't know, have you used the data to see this kind of results?
I guess a couple comments. One is that I think for me, one of the main goals is to understand what the profile looks like. So in other words, it's for this type of modeling exercise, it's really important to understand what the average composition looks like. So that's motivated a lot what we've done. It's clear that I think in terms of actually looking at emission rate, in my mind, you need a much larger data set to look at that. So, I mean, there's been many cases where we looked at emission rates, comparing those and trying to understand that versus the average composition. And so I think there certainly are some trends in there, but I personally feel that before we made any sort of conclusions about emission rates, I think we would want to, move beyond a 60 vehicle fleet and try to get a lot more data for that. And I think that's true in general when you're talking about trying to look at relationships with emission rates versus emissions rates with relative composition, if that makes sense.
Yeah. Thank you.
ARB has a pretty aggressive program to reduce diesel PM through new vehicle standards, cleaner fuels, and retrofits. And one thing we don't have right now is the ability to monitor the success of this program independently of emission testing, through ambient data, because we haven't had a molecular marker for diesel. But Eric, I think one of your conclusions was that you could use EC as a marker for diesel. And I know, Jamie, you wrote a paper a few years ago that said you couldn't use it as a marker. And I just wanted to see if maybe you could reconcile these two apparently contradictory statements.
I think the key thing, and in that paper, it says it talks about LA specifically, and I think one of the important points is that if you account for the EC from other sources, that in the context of the gas diesel split, it's very powerful. But in other words, if you're sitting in downtown Beijing, and I've taken a lot of measurements downtown Beijing, clearly a lot of the EC there is due to coal combustion. Likewise, if you're talking about other periods of the year, not the summertime, where the wood smoke is very high, even though the EC may only be 10% of that, like in, for example, in the IMS 95 study, then obviously EC is important from wood smoke. So I think the issue is that if you went out blindly measuring EC and said that's diesel, you're going to get in trouble. But if you could have other supporting data that accounts for the amount of EC from those sources, then you're okay. And it turns out in this study where wood smoke is small, fuel oil combustion is small, coal combustion is small, then EC is a pretty good surrogate for that. And I think the paper says that. I'll have to go back and read it.
Well, I would add to look at long-term trends in contribution of mobile sources to ambient PM. You can look at an ambient monitoring site, but the signal there is fairly low because things are fairly dilute, and as we know, the concentrations from the roadway dissipates very rapidly. So I think one alternative approach would be to make on-road measurements, much like what Dane and Scott has done and we have done in the HEI study, where you drive a prescribed route several times and do that regularly every year or maybe every other year, where the concentrations are easily an order of magnitude higher than a typical monitoring site. And there you can monitor what the trend in concentrations are in those environments.
And I would add one caution, I think, even with regard to the on-roadway studies, in that when you're on a freeway and driving along, you're with the flow of traffic, and so you're really just measuring the immediate environs rather than a whole bunch of vehicles passing by you. So if those emissions are really influenced by, say, a high emitter, you might miss that high emitter just because you're on the freeway avoiding the high emitter or not nearby it. So there are strengths and weaknesses to each of these methods. Now, I think the thing that we see that's very good about this study is you need to realize, and maybe we didn't emphasize enough, that Eric and Jamie were doing these apportionments independent of one another, and so not until, I guess, about 3 weeks ago had either group seen each other's results. So this was done in a blind fashion. They both took different approaches, as you see, and we're getting somewhat similar results. What we're seeing is the importance of high emitters and how they influence the data. We're seeing how the ECOC can influence the outcome of the apportionments. We also see how powerful the day of week analysis is, because there's so many fewer trucks on the road on Saturdays and Sundays. It turns out to be a very important tool for doing apportionment of PM. And people now are looking at, as I'm aware of, in different parts of the country. Jamie published a paper about a year ago from St. Louis showing day-of-week differences in PM. So you can use these methods now to get more information on apportionment. And what we really need to understand is how important and what the sources are of that unidentified organic carbon and where that's coming from. And I guess my bias is it's coming from either gasoline or diesel fuel or lube oil or all three of them. But we need to understand a little bit more about that too. And I think Jamie has an email question.
Okay, this is an email question. It says, what is the importance of the population of smoking vehicles? According to Dr. Schauer's work, the weighting of the SI profile to account for the different percent smoker seriously affects the apportionment. Is there a tipping point insofar as a percent smoker in the SI fleet beyond which the apportionment is completely unstable? I guess I think for me, really the key answer to this is it's not so much the percent amount of smokers, but really it's the question of how some of those very, very different smokers, how important they are. So, for example, if you were to believe that some of those extreme smokers that are very high EC or have very low amounts of these tracers, then that would have a very large effect with not very much. My gut feeling is, but I don't have the data, is that it's not those smokers that are the typical smoker out there. It's but I think we really need to have the data to say that. So I think equally it's not the amount of smokers, but it's what is the distribution of the composition of those smokers, if that makes sense. I don't know if Eric or...
Okay, any more questions?
Well, I have a quick question again. I'm interested in the speciation data. So you said there's a website, they post the data on the website. Do you have speciated data?
Yes,
there?
the data that you've seen today are all posted at the NREL website, and it's all available right now.
Great. How about the VOC side? Do you have VOC speciated, fully speciated?
No, we don't have it. DRI took some data that Barbara Zelinska did some speciation that aren't part of this, but maybe part of the... Eric can answer that, but the air toxics we do have for 28 vehicles. So that's a gas-phase species. And there is a little bit of information on the other compounds as well. And I don't have those at the site yet, but we'll work on that over the next month.
Thank you.
To clarify any confusion, there were two sets of volatile organic speciated data collected during the gas diesel split study. One is what Doug reported on. That was done by EPA using, was it bags or canisters? Canisters. There were also a set of VOC data collected on site with a GCMS within a few minutes after collection of the sample. In that case, there is no problem with 1,3-butadiene. And that data was collected for the CRAPEX program and should be available already. That was reported, that was done jointly with CSERT. And I think they have a report. Is that right, Karen?
Yeah.
Okay, well, let's thank our speakers for a very interesting seminar. And I'm sure they'll stick around if you want to answer any or ask any questions one-on-one.